Okay. Hello, everyone. My name is Jacopo Poli. I'm the CTO of LightOn, and I'm happy to introduce Guilherme Penedo today, who is a next LightOn employee, worked in the Falcon team, and is also the lead author of the refined web paper, and is now a machine learning engineer at Advantes. He's continuing to do work on pre-training data at scale. And we decided to invite him to talk about just that. So, Guilherme, the floor is yours.
Okay, so hi everyone. Let's just see if I can properly share my screen. Can you let me know if you are watching the presentation in full screen?
Yes, we are.
Okay. So as Jacopo just said, I'll be talking to you guys about pre-training data for LLMs. He has already introduced me, but you can find my social stuff in here if you want to reach out. You can also email me if you have any questions that I don't get to answer today. So just like for a brief overview of what I'll be talking about. So I'll start with just some general high-level view of how, like the different training stages for LLMs, and then we'll go deep into the data, why it matters, how much data you actually need to train an LLM, before going through some, like concrete steps that we run when processing data, and then how you can check at the end, like, is this what I've done good? Like, how do you check the data is good before just scaling up and training a very large model and committing a lot of money? And finally, I'll walk you guys through a bit, like a quick intro to Datatrove, which is data processing library that I've developed while at Hugging Face, and that is open source, which means that you guys can use it for your own projects. So starting with this overview, so basically, you probably already know this, but there's multiple stages in the like a life cycle of LLMs. We have this pre-training stage, which is by far the most expensive. You're basically just giving a lot of data to general data to a model. You have instruction tuning, where you're trying to change a bit the way the model handles predictions, right? You don't want it to just complete your text in a very naive way. You want it to answer questions, to perform the requests you ask it to do, and so on. You have then an alignment phase. Like this can be, depending on what you're doing, can be quite expensive. For example, like for the ChatGPT models, this is probably quite expensive if you are using human annotators, especially, where you're trying to align how people use the model, like what they expect the model to do to what the model actually does. And then there's some things like you can just try to get the model to perform different tasks by just putting things on the context. So in the text you give the model, and then there's like some very like downstream task specific adaptations you can do, and there's like some very efficient methods to do this currently, like LoRa's and all this stuff. And obviously, like as I just was mentioning these different stages, you can see like they have different goals, they have a different costs, and the data they use for each one will actually also be quite different. So like why should we care about like the training quality of data for LLMs, especially for pre-training? So like something that is quite common when people get into the field is like they're just thinking, like I should, maybe if I research and I check and I investigate, I can find an amazing new architecture that will just beat transformers, they'll beat whatever other architecture there are, and it'll be amazing, and we'll have AGI and all this stuff. And the truth is, like, maybe like this could happen, sure, whatever, but is it likely? Not so much. So here I have like a little blog post, an extract from a little blog post from an OpenAI employee. This was doing the rounds on Twitter when it came out, and like basically what he's saying, which is what in my experience is also pretty true, is that like even if you have different architectures, or like have a special it's an optimized hyperparameter, whatever, in the end, the thing that will make the most difference is the data quality. So like for the same data, just training long enough, usually on different architectures, if they are like reasonably good, there won't be a big difference. What will really make a difference is the data that you are training the model with, right? It's the common garbage in, garbage out that people say. So like this is why you should really focus on this quality. I also have a little extract from a recent paper. So this is from the Yi paper. So this is a family of Chinese developed models that really topped the OpenLM leaderboard when they came out. And I mean, what they say, it's also like echoes this idea that the underlying assumption is that when trained on extensive data of high enough quality, a standard architecture can exhibit advanced capabilities. So again, the focus on the quality of the data you are training your models with. okay, so we want good data, but how much of it do we need? And I would just give you a brief like historical context here. So like a few years ago, people were starting to try to answer this question: if I have a given amount of money I can spend to train a model, which we call the compute budget, how should I size the model? What model size should I train, and on how many tokens? And there was this, people came out with these things called scaling laws, which basically tell you, like, for this amount of money that I want to spend, how large should the model be, and how much data should I train it on to get the best possible model I can get with this money, these number of flops, this compute budget. And there was this paper from, I think it was from OpenAI, scaling laws for neural language models. So it's already quite old for machine learning standards, which is from 2020. And they were saying, you should just scale model size, number of model parameters much more than data. And you can see here, like the increase in model parameters is huge compared to the way they are increasing data. So as a result, people were training bigger and bigger models on not a lot of data. And you can see some examples like even GPT-3, 175 billion on 300 billion. And then you had like some huge models, even like Palm, which is not listed here. We had models with 500 something billion parameters trained on not even a trillion tokens. Until there was another paper called the Chinchilla paper. I mean, not called Chinchilla, but the model that introduced the Chinchilla model. The paper was called Training Compute Optimal Large Language Models. This is a paper by DeepMind, and they re-examined these scaling laws. So basically, you have these different curves where you have the same compute budget. So meaning, for a given amount of money, a given amount of flops, they train different models with different parameters and data sizes combination. So, but like the two give the same for the same compute budget. So if you increase the model size, you have to decrease the data size. And they checked, and basically, like this is, so on the y-axis you have the loss. So obviously you want to minimize the loss. So you can see that there's these little points. Here are the points where you want to be, and this gives you like the size, so the model size for and data size for each compute budget. And basically you have a more or less linear relation. So the idea here is that you should scale data more or less to the same scale you are scaling your model size. So this is why like they trained this other model, Chinchilla, in this paper, and they trained it with the same compute budget as their other model, Gopher. So you can see Gopher was trained on 280 billion parameters with 300 billion tokens, whereas Chinchilla is much smaller but trained on a lot more data. And actually, like Chinchilla completely crushes Gopher. So like with this, they showed that the models that so far were being undertrained, meaning we're not giving enough data for the size of models that we had. There's something else to consider. So there was this phase with the Chinchilla scaling laws, and a lot of models, including Falcon, for example, they are compute optimal, meaning for the compute budget that we had to train, we trained the best possible model size and dataset size combination. But there's this thing where in the real world, people want to deploy these models, they want to run inference on them, and running inference on a 180 billion parameters model is not really nice. It's very expensive, obviously. And as you can imagine, this inference costs will go up with the size of the model. So ideally, you would want a smaller model that is really good, meaning that you can save money once you want to deploy and run inference on this model. So there's this inference training compute trade-off where people started doing something different. So instead of training the best compute optimal model size and dataset size combination for their budgets, people started overtraining their models. So meaning they they would train a smaller model for longer, right? And the idea is that since you'd get a worse model with this combination if you were to keep the same budget, so like the same size and dataset size, you have to actually scale the dataset size a bit disproportionately to the model size. So like you basically train for much longer, which means that you will end up actually spending more compute on the training than if you were to train the compute optimal model. So basically the trade-off here is that inference will be cheaper, so you'll be spending less compute on inference at the cost of training or for longer and with a bigger budget for training. So what this tells us, and if you look at some of the recent models that have been coming out recently, such as the Llama 2 models last year, I think, and for example, the Mistral models, they are trained for much longer. So even for smaller models, and we're talking like even, like not even 30, but like 7 billion models, people have been training them now for trillions of tokens. So now, like, I mean, I'd say at a bare minimum, you'd need like a few trillion tokens to be able to compete with one of these top companies, assuming you have the capital, because this is a very capital intensive thing, training models. And as an example, you can see Llama 2, and you can compare. So like, for example, they trained a 7B model on 2 trillion tokens, which, I mean, was just insane compared to the previous things that we were doing before with very big models trained on not many tokens, then, more or less balanced. And now it's the opposite, smaller models trained for longer. So yeah, so basically we need a few trillion tokens. How are we going to get these tokens? So just to as some context, if you don't know, like token, you can think of them more or less as words. So what we want to do exactly? So if we want to think about what we want to do to process our data, we should think about what the goal here. So we are pre-training a model. So we are this initial phase of a large language model where we want it to be a good model, like in general, so across the board in all sorts of different tasks. So we have to have like maximal coverage of like many different domains, and we need a lot of text, as we saw recently. So what are some challenges we'll run into? So we want to maximize diversity and coverage to have this general purpose idea thing. We want to maximize the quality and robustness of the data. So we would prefer not to give the model trash. Again, because trash in, trash out. So yeah, if we can, we should try to give good data to the model. And then there's some other skills, some other challenges, which is, okay, but what is like good quality data? How do you measure if your data is good or not, especially at this very big scale? And then there are some other issues, such as like, okay, but then I have to process a lot of data. How can I appropriately scale my infrastructure, my code? And this, for example, like this is one of the challenges that Datatrove tries to answer. So it's a public library that people can use to easily scale the processing to thousands and thousands of CPU cores. And so getting on with this, like, so where do we start from, right? So where do we take our data? Like, there's all this data that you need, but where are you getting it? Obviously, you're not writing it yourself, so there must be a place where you get it from. And usually it's from the internet, and more specifically from two sources. So if you're doing general language and not code specifically, usually you start from Common Crawl. This is an open source foundation that has been crawling the web every month, pretty much since 2008. So they have an enormous amount of text, but obviously, the web in general is not good. The average quality of a website is not amazing in terms of text quality. So you'll need to take this data and go through multiple steps. If you're doing something that, like, if you're training a model that you want to be good at code, for instance, you should include some code from GitHub or Software Heritage. And again, like, code would have different processing steps specific to code. And then usually you want to include some specific created corpus, such as like you want the model to have all the latest knowledge. So you just give him the latest snapshot of Wikipedia, some public domain books. Some people historically have given copyrighted books. Then there's more the legal side that comes into the issue. And more recently, there have been new trends with training models on synthetic data. For example, the famous Phi2 models from Microsoft were trained with synthetic data. So basically, the entire training data of this model was generated by another bigger model. And they actually are pretty good at the benchmarks. Since the data is not public, it's hard to say if it's because the data they generated is just too close and similar to the benchmarks, or if it's for something else. I'll let you, you can try out the model and judge for yourself. Okay, so we have our data from, for example, Common Crawl. So what do we do? So there's three main, groups of steps. You first take the text. You possibly extract or parse this text if it's in some other different format. You filter the data set. So you have a lot of data. You will want to find, some specific samples, documents in this data that are not good quality, and you want to remove them. And finally, there's a big step as well, which is the duplication. So basically, and I'll get into this a bit more further on, you want to find matches of similar documents or the same documents that are repeated over your dataset, and you want to remove a few of them to make training more efficient. So while the filtering step is something you can usually run in parallel, right? Because you just look at a document to decide if you should keep it or not. For the duplication, you're actually doing matches between all the documents in your dataset. So this is usually the more engineering-heavy and costly step in data processing. So how do we start? So like we have our text, and I just will walk you through different types of like filters, extractors, and so on. And like specifically Common Crawl, they give you data in different formats. So you have the work format, and you have the wet format mostly. Whereas the wet format is text, pure text data. So it's something you could give to a model to train on, and a lot of people do. You can see they have, for example, for this specific month of Common Crawl, they have 9 terabytes of data for this wet format. You can see that there's an order of magnitude bigger for the work format. So what is this work format? Basically, the data in work format is the raw HTML from a website. So you go to a website, you right-click, you click on Inspect Elements. This is what you have in work. And then through some automated process, Common Crawl tries to extract the main text from this HTML and saves it in the wet format. The thing is, from some experiments I've run in the past, we are not super happy about the text the quality of this text extraction from work to wet. So we prefer to start from the work and run our own text extraction. So for this, we use a library called Traffilatura. So basically give it HTML, and we'll, through some heuristics, such as, for example, if you have a navigation menu with a lot of links, it will try not to include them because you don't want the menus, you want the actual text, footers, and so on. So it just tries to select HTML elements that could have the proper main text of the document and extract it for you. Usually, one of the first steps as well is language filtering. So if you're training an English language model, usually you'd want to only include, or mostly only include, English data. So you could, what people mostly use are some fast text models. So this is some small fast CPU models from Meta that you can train yourself, or you can use some already pre-trained models on with different languages of Wikipedia. Apart from this, you could also try to do something such as looking at the URLs of the documents. Like if you have a website that is .fr, then you could assume that the text is in French, for example. So there's different ways, but the bottom line is you'd want to select the specific, split the data into different languages. You have a bunch of filtering processes focused on heuristics. So what we mean by heuristics is that these are specific handmade, handpicked rules. For instance, you could have something that will try to count, like how many words you have per line, how many documents you have, like that have fewer than some number of words. You can see, sorry, you can see some, like for example, look at some ratios. So you could take, for example, a document, you compute what percentage of this document consists of alphanumeric characters, how much of it is actually just symbols, and so on. And based on the specific threshold, you would remove or not the document based on these ratios. And there's other things you can do, like you can check for repetition. So if you have a line that is repeated like 20 times in a document, you could remove this document, and so on. So these are basically rules that someone looked at some data, they thought about it. Maybe we should try to remove these types of documents. So they wrote some code that will try to catch them with this specific handmade rule. The table is from this paper, by the way. So what are some advantages? So this is very controlled. It's very clear what is happening. Like they are specifically removing things that have this specific ratio above a threshold. And it's quite clear, like usually you would not be introducing a lot of biases in terms of removing underrepresented content from your data set, for example, because you're just looking at the ratio of special characters or some other things that would be, probably catching more like ads and websites are just trying to spam keywords to optimize search engine results. On the other hand, this is quite surface level, so you're not looking at the actual content. Usually, you're just looking at some specific rules, right? And there's this other difficulty, which is you have to set the threshold. So what is the acceptable number for the specific ratios, so that you don't remove too much, but neither remove too little, right? And then obviously there's some other filtering where you can use ML itself some ML methods to remove some data. So For example, like the language filtering we mentioned before is an example of this. But you can have other classifiers. So for example, you could have something to classify, if some context is toxic or not, if it's like say for work, if it's something that should not be, like something else. And you can even, so some other people do something else, which is they train, they look for perplexity on a given reference corpus. So for example, we train a model on Wikipedia. And these are very small models, by the way. They're not an LLM, they're just small models that run on the CPU. So you train a model on Wikipedia and you check the perplexity of this model on a document. And basically with this, you could more or less decide if you can more or less tell if a model is written in a style similar to Wikipedia. Obviously, there are some other disadvantages here especially compared to the previous methods, which is that there's quite a lot of content that is not written in the style of Wikipedia that you would probably still want to keep, like more informal content, more like conversations that happen more naturally, all this stuff. It's probably not going to, with this filter, it would probably not be kept, and you probably do want to keep it. So when you're using these ML filtering methods, because it's very easy to introduce some bias in what you're doing, but it's also like easier to control in terms of you want to remove some toxic content. You don't have to list all the toxic words that exist in the dictionary. You could just give the model some examples and train a small classifier. So there's always a trade-off, right? So just some general notes on filtering. So you should be careful of domain-specific points. So for example, something that is still nice to do in the end, even if you have a lot of data and you obviously can look through it all, you should still manually inspect some of the data. So for example, you could try to extract the top 10 domains from your dataset, check what is specific from this website, check how it's being parsed, filtered, and so on. And you could even see, okay, maybe for this website, there's this sort of data that is being kept that should not, so you can craft specific filters. And especially if you're looking at different languages, you can't just blindly transfer your English pipeline to a different language because, all these thresholds could be different. For example, if you're running on German, like the average word length will probably be bigger because you have a lot of composite words. So you have to always be mindful of this more like actual impact of what you're doing. Finally, there's another approach here you can take, which is instead of just being deterministic in terms of, okay, everything that goes above this threshold I remove, you could have a more stochastic approach where you say, okay, like if the filter is triggered for this data, then I'll keep maybe 5% of the samples that trigger this thing, so that we might try to avoid a bit the bias by just keeping a bit of diversity. Even, like maybe that is not good, but you don't know exactly what it will be, right? So you could let some of the data through, even if they trigger your filters, instead of just having a very hard threshold. And then the duplication. So we've spoken about filtering, which is this main thing you can do in parallel. You look at each document independently, you take a decision, you keep it or you drop it. But then obviously we have this big data set and you want to train a model on it. And there's this other step called the duplication. So why do we do duplication? Why does it matter? So, in the web, there's a lot of websites that just copy content from other websites. There are websites that, for example, use the same software. So I could tell you when we were creating the refinement dataset, we saw that there was like a cluster of documents that had the exact same text, and we had like millions and millions of these documents, and they were basically from a WordPress plugin, from some sitemap WordPress plugin, saying this is the sitemap WordPress plugin developed by whoever, and you had this document millions of times. So, like having these very big clusters, you basically just increase. You have this very high distribution density around these clusters, which is reducing your diversity, especially if you're sampling from your dataset. There's a high chance that you'll be just taking a lot of that data and not covering as much as you could. There's also this idea that has been researched quite extensively that models memorize data quite quickly, so you don't have to, like give even if there's something you really want the model to know, you don't have to give it like thousands of times. Once or twice is enough. So the duplicated data is actually much more likely to be memorized, and then you have the model just spitting the exact same thing as was in the document, and there's no need for this, right? So, and then overall, this is the idea that I find the most, like the one that most resonates with me, which is you just have a lot of data, you're training, you have this is very expensive GPUs you are training on, and you are giving the same document thousands of times. How is this efficient? How does this make sense, right? You want to, one of the main reasons why you want to duplicate is just to have training be more efficient, because if you remove the duplicates, you can cover more diverse data set, more like a bigger variety of data with the same compute. So it must be better in terms of, and indeed it is better usually, like you get a better performance on downstream tasks when you run the duplication. And then obviously there are some other different methods for duplication. So there's not just like a switch, you know, okay, the duplicate and it goes. There are different methods, they do different things, and there are different trade-offs between each one. So I'd group them in two main categories. So you have fuzzy deduplication. This is where you try to find similar documents, and obviously there's not a clear definition of what, you know, how can I say if two documents are similar or not? Like, so each method and then each parameters of each method have a different way of defining this. But you have, for example, room filters, where you basically have a big array. For each document, you create hashes and you check if they exist in this array. And if so, you assume you have seen this document before. You have min hash. Min hash, you take the set of n-grams. So you basically take, you know, every group of 3 sentences from a document, for example. These groups of 3 sentences between different documents. And obviously, because it's so very slow, you use some hashing techniques so that you don't have a very like n squared process, which would be very slow. You have something that is becoming a bit more common, like you can try to embed the data, cluster it, and try to remove some documents that are very similar semantically, for example. And then you have a more exact approach where you can just, so one very, it's not brute force because it's still optimized, but you can just, you know, okay, I'll take my entire data set and I'll find exact matches between specific strings. So you can just create a very big suffix array, and this takes a lot of memory, a lot of RAM. And you just go through the array and you just find duplicates. You could try a more granular thing, like on the line or sentence level. So you take each line in the data set, you hash it, and you try to find matches between different documents and different lines. And then some notes on this, like, so as I said before, this part is not parallel. So you're actually comparing each document to every other one. Maybe not explicitly because you're not doing something dumb that is O(n) squared, but you're doing, you know, like in any case, in the end, this is what you're doing. So you can't just look at a document and decide if it's a duplicate of a different one. You actually have to look at all documents and do something with the results to find these matches. So this is obviously much slower and much more expensive, right? You still have hyperparameters to tune. As I was saying, it's not like a magic formula. So for example, for min hash, the way you choose, because you take a bunch of hashes and you split them into buckets, and the way you choose these hashes, these bucket sizes will change the probability, because again, this is not like, this is a fuzzy duplication. This does not guarantee that you'll find matches, especially because you have this hashing technique to make things easier. But you still have hyperparameters to tune, right? And this will affect results, to affect how much you remove, how, for instance, if you have a very big data set and you're basically clustering similar documents, and you have one document that is similar to a different one, and this one is different to a different one, and so on and so on. Whereas, you know, the first document and the last in this chain are completely different. Since you had this little chain of gradually changing, they would all be matched to the same cluster. So you have to be very careful with these hyperparameters and what you're doing. And unfortunately, this is very hard to inspect because you can't just look at one document and see, okay, it was removed. You have to look at the actual cluster, the actual match, the actual whatever caused it to be matched to some other document, and that caused it to be removed. And some are more expensive than others. Obviously, you know, like this method of just having a very big suffix array is very expensive memory-wise. At some point, we were using this for refined web, and we had an instance that had a few terabytes of RAM, just so we could, yeah, and I mean RAM, not storage, like actual memory, just so we could keep the whole thing in memory. Min hash is the most commonly used one. In most papers, people take a specific amount of n-gram size and a different number of hashes and buckets, and then they run min hash. And again, as I was telling you, I mean, these methods are approximate, so there's no strong guarantees. And while semantic and embedding-based methods are interesting, they're still a bit expensive and very slow at scale. Now I'll just walk you through an example so you have a clear idea of how you can, you know, like what would be one pipeline. So this is the example. This example pipeline is the one used for refined web. So we started with our common crawl text before even looking at the text. And as I was telling you before, we use the HTML version, not the text version. We started by looking at the URL. and we were performing some filtering based on the URL. So we took a list of like pornography websites from the internet, gambling websites, and other like scam websites and so on, and we just matched these to the URLs from each sample. We had a specific word list to try to match different things, but only in the URL, again, so without even looking at the text. And this already removed toxicity by quite a lot. And then we performed the XML extraction. So we use Traffic, we get the main text, we filter out anything that is not English. And this already removes like 50% of all the documents in Common Crawl. And then we apply some of the rules-based heuristics filtering. So we have some rules to try to find if a document is just the same sentence, the same group of words repeated a lot of times. We have some rules to try to look at ratio of symbols, length of lines, to detect quality. And everything here is, again, runs document-wise, so we look at one document individually. We have some specifically handmade corrections for some lines. So for example, in some lines you'd see share on Twitter at the end, and this is just an artifact from how the HTML was parsed. So we have some handmade things to try to correct a few of these by hand. And again, with all these 3 steps, you also remove 50% of the original, of the 50% you had after the language ID. And then duplication. So here we use the setup from this paper from Kathleen Lee called Duplication makes training models better, makes models better. We start with min hash followed by exact substring. So first a fuzzy approach that scales quite well, followed by the exact substring to find exact matches. And in the end, we ended up with like 10% of the entirety of Common Crawl. And you can see how much each step removed. So starting with URL filtering, which doesn't remove much. And not language, which removes 50% of the non-English data, and so on and so on. And by the end, you have the duplication, and you end up with like 10% of the original data. So refined web, just for some context, is the model that was used to train the Falcon. The dataset that was used to train the Falcon models. Some other recent dataset papers. So unfortunately, there are not a lot of dataset papers now, because even if you have some open source models or open weights models such as Llama, Mistral, usually the data itself is not public. So they give you the weights, but they don't give you the data or the code to recreate the data sets, or sometimes don't even tell you how much data they trained on, right? So it's all a big mystery. And this is actually this paper from this multilingual Chinese English data, this model I was telling you about before. They actually have this setup. Sorry. So where they do some language filtering, they do some heuristics-based filtering as well. They actually do some perplexity filtering, so the ML method, and then some different duplication steps, paragraph level, min hash, and exact substring. And then they also do some more ML filtering, so they have some models to detect unsafe documents, to detect, for example, ads, which are overrepresented on the web and usually are not that interesting, and so on. You have a similar setup for this is the Doma paper, also quite recent from Outperforms AI. Okay, so now, we have all these steps. How do we know if we're doing the right thing? So how do we know that the data we got at the end with this other new filtering step is actually better than before, right? So how can you measure this? So, like in the end, usually, so before people were testing things they were just checking the loss and the perplexity of the models. Nowadays, people mostly care about benchmarks, and some people say that even benchmarks are not good enough, and you should just have something like the what is called the LLM arena, where you can compare results from different models blindly and use that to check which model is better. But anyway, what I usually do is I train some small models, because like if you had a function, like it would tell you this document is good and this one isn't, then you just use that as your filter, right? You wouldn't have to do all this stuff. So obviously that's not the thing. So what you can do is you take your data, you train a small model on this data, and you evaluate it on these tasks and benchmarks. And so obviously you don't want to spend a lot of money on this only like experiment model. So you train a small model. And if like for 1B, the compute optimal dataset size would be around 30 gigatokens. And then you try to identify a set of high signal benchmarks. So what I mean by high signal, I mean something that at a small scale and train on not a lot of tokens already gives you good results without a lot of noise. So you have this two different ways of trying to identify these tasks. So we have one that we use, for example, on Falcon, which is the low variance approach, where you want benchmarks where obviously the results are above, random baseline. So if you have a multiple choice for options task, you want results at least above 25%, right? Otherwise, the model isn't doing much. You want something that where doesn't have a lot of noise. So if you train twice, for example, on different parts of data or on different visualization of the model, then the results are not like significantly different, right? Because if they are, then you're not. That's just noise. That's just evaluation noise. You're not actually measuring how good your filtering process is. And finally, you can also check, like for example, between different data sets, if on the specific task you don't have a lot of variance. Like for example, if you train a few times on the pile and a few times on C4, there's not like a huge. The variance between the two is more or less the same. And there's another way to look at this, which could be, okay, so you want something that is good, like at a small scale, so you could just take a few checkpoints as you are training, and you want something that is pretty much always increasing as you train more. So something that isn't going up and down, like something that is monotonically increasing in terms of accuracy or whatever metric you have. And so this is the benchmarks that we currently use for this high signal subset of benchmarks, Common Sense QA, HelloSwag. So HelloSwag is quite good usually. MLU and so on. Even though MLU has a bunch of subsets and some don't work as well. And then there's some like specific details on how you implement your evaluation codes. So something that is good to keep in mind is that you shouldn't. It's harder to compare your results with your evaluation benchmark with the results from some paper because they were not evaluated in the same way. So usually what you should do is, if you can, is you should evaluate the other model with your own codes, with your own evaluation codes, evaluate your own model with evaluation code, and then you can compare. Because even the way the question is prompted, if there are letters for the option names, if you're just using a normalized log likelihoods to check which one is better, or if you're using something else, all these make a difference in the results you get. So it's important to be consistent with the evaluation suite you are using when comparing different models, different processes, different filtering steps. So I mean, this is the mostly I'd say the high iteration, like the process that gives you a lot of like a very high iteration rate on development. So you can try something new and you implement some new filter, you apply it to your data, you tokenize it, you run a model. And this is a small model, it trains quite quickly. Running evaluation on only this subset of tasks should also be quite quick. In the end, you can just get an aggregate result. You have a number, you can compare it to before, you can iterate and try something else. So this is I'd say it's a good pipeline, especially if you have the whole thing automated, so that you launch the training, it then launches the evaluation by itself, and so on. But you can also do some other things, like, okay, so you could do some manual data inspection, as I mentioned briefly before. So you could, for example, look at some top domains and URLs that are overrepresented in your data set and what they consist of. You can, for example, look at what documents you are removing at each filtering step. And you can try to search, for example, like if there's a specific, you can look at the top, like the most common phrases, the most common characters, whatever, and try to search and see where this is coming from and what it is. You could also try some like clustering methods. So you could, for example, this is a picture from clustering some documents in a web dataset. And you can see, like, you probably can't see because it's too small, but there's a big cluster of, for example, spirituality. There's a big cluster of project management, marketing, and so on, which is the big ads stuff. And then you can also, there's some other stuff you can do, like just look at the training and tokenizer and looking at the largest and smallest tokens. So yeah, I mean, I hope this gives you some good idea of data quality in general. I'll now tell you about Data Trove quite quickly. I'm not sure how we are in terms of time, but basically this is a library that will, allows you to take care of a lot of this work for you. So it implements a lot of these very common filtering, duplication steps. So like the code is already implemented, you can just import it and run it. And also it scales quite well because, like the same, you specify a pipeline. So you specify a list of steps you want to run, and you can run it locally or on Slurm or on something else without changing the list of steps themselves. Okay, and you can you can get data from S3, from locally, from the Hugging Face hub, from some other cloud provider through FSspec. Sorry. So it's quite nice. And I mean, so this is the library. It's open source. I told you, you can go to github.com Hugging Face the Trove. And I have a small collab notebook just to walk you through. I can probably give you guys the link to this and even the slides afterwards. So this just installs the library. So you have, this is the main data structure. So basically each sample, each document has a text, which is a string, has an ID, which is what should be unique across the data set. And then you have anything else you want to, just like in the metadata. So this could be the language, it could be the URL, everything else goes in here. This is me defining documents manually. So this is a document with this text and this ID. And if you print it, this is a data trove object. You have a bunch of different pipeline blocks. So here, if you go on the code and you see the trove pipeline, you have blocks for the duplication, for text extraction, filters, blocks to read data from different formats and sources, some for statistics, tokenization, and to writing data back to disk. And so how do you define a pipeline on data trove? So basically, a pipeline is just a list where you import different steps. So for example, I have a reader here that would read my data from a specific folder called sample data CSV samples. It would sample, so it would keep, like data with a 0.6 probability rate, and then it would just write it back to some other place on disk. So, like I'm not doing any listing files, opening the file, reading each line. All this is abstracted away. I just use the reader. It reads my data. I do some filtering with it. I write it back to disk. That's it. I don't have to worry about all the low-level implementation steps. So how do you run this thing? So this list. So the easiest way is to run locally. So you can use a local pipeline executor. So basically, you give this pipeline this list of steps, which here is a bit different. So here, what I'm doing is I'm reading some data that is in JSON-L format. I am filtering the data to only keep the data in English. And I'm writing this filter data, so the English data, to this folder. This is where I'm saving my logs, because this thing will save logging statistics and other logging info. I want one task because I only have one file, but usually, when I'm running actual jobs, I have thousands and thousands of files. So I would have, like a few thousand tasks, and the reader will actually distribute the data across the different workers so that each one has a subset of the total data, and they can run in parallel, and the thing will run quite fast. And here, this is something else. But basically, if I take my executor and I call run on it, you get all this output. So you can even make a script and just call Python, and then my script to run things.py. So this is the pipeline steps we have. This is the output. It's reading the file, and this is actually like a very small file, so the thing finished almost immediately. And you can see the stats for this specific task, and then the merged statistics, which is we have single task, it's the same. So you can see, for example, we ran one input file, which is this file here, the 00000.jsnl.jz. In total, there are this number of characters in this file, and it's the text field of this file. And you have the minimum, maximum, and like the mean and standard deviation per document. You have the number of documents, so you have 184 documents in this specific file. We run language ID, so this actually took the majority of the runtime because we're actually loading a small model, whereas here we're just reading and writing data to disk. But still quite fast. So this is how long it took to run per document. We took the 185 documents. We kept 168, and this is again the length and average length of the documents that were kept. So obviously 17 were dropped, and then this 168 that were kept were written back to disk. So here I have the compression none option, just so we can look at the output data. So if I were to open this English data file, you can see it's all English. But let's say I want to save the data that was removed. So I want to see what else is there that is not English. So if I uncomment this other parameter called exclusion writer, which is a parameter that all filters have, I have a writer, a JSON writer that will save data to in JSON format to this other folder, and we can run again. So I have the skip completed option because if we go into the logs folder, it was created for this job, and like you also have the stats that we saw here in a file in JSON format. You have the stats for each individual task. There was only one, the logs, and so on. You also have a completions file. So basically, since this task completed, if I were to rerun the pipeline, I can actually run it like this. You will see a message saying, not doing anything as all, one task has already been completed. So this is nice because sometimes tasks fail, especially if you're running thousands of them, have a node that fails, you have something that goes wrong, and like your 90% of your tasks completed, the rest didn't. So which ones didn't, you just, the Dataset will look at this folder and we'll figure it out. But I actually want to run it again because it's a different thing, so I'll just ignore this. And if we look at it here now, and we see on our folder called other langs, so other, which should be here somewhere. Yep. So if you look here, and we have this data, and you can see it's actually not English. In fact, it's actually Portuguese. And if I were to add something else, so basically this filter adds a field on the metadata of each sample that has the language, and I can use that specifically directly on the outputs path. So basically, I want to create a folder inside this thing for each language, and then the files in there. So if I run it again like this, you can actually see, and I refresh, there will be a PT folder for Portuguese, and if I had other languages, there will be a different folder, and each folder would contain their own languages content. You can also use Dataset programmatically, so I could import the graphical to a block and run it directly on text. So for example, the HTML text I had above, or you can just give it a list of documents and it will process them all. Or if you want, like you could also, if you want to easily read data from some other source. So for example, I'm reading data in Parquet format from a Hugging Face dataset. So this truthful QA, which is an evaluation dataset. And we have this Parquet file here. So I have a Parquet reader reading from this path directly, okay? And I want to save the text that is in the text column. So if you look here, it has multiple columns, and one of them is question. And that will be my text key, so the text column. And I'll open a JSON writer to save it somewhere else. And then, like I'll just, for each sample, I'll just write it there, but I could do something with it before saving. And if I run this, you'll see that there will be saved from hub. So where's this folder? Oh, yeah, there it is. And you actually have the dataset here. What happens if you eat the watermelon seeds? And these are all the questions that were from the datasets. You could also load data from S3 directly, so no need to download it beforehand, and so on. And like just to finish off here, you also have a bunch of different examples on the README. So for example, you could have custom functionality, so you can create your own blocks. And you could also see, for example, if you want to run the duplication, you have some example pipelines to run min-hash duplication. So there's quite a lot of steps. But they are explained, and some other things. So yeah, I mean, I think, yeah, just some other tools, like in case you'd like to do some of these things by yourself, like you have a training framework, even though this is more like if you want to use, like if you want to train a very large model, because it has like a built-in tensor parallel, 3D data parallel, all the 3D parallel stuff. There's a evaluation framework from Hugging Face as well, and some other libraries that you can use for different things, if in case those are helpful for you. And that's it. I mean, I'd just like to thank Tom Wolf, so the CSO from Hugging Face, for letting me borrow some of his slides. And that's it. If you have any questions, I'll be happy to answer them.
Thank you, Guilherme. Yeah. Does anyone have any questions? You can either unmute yourself and ask, or write them in the chat, and I'll ask them for you. Don't be shy.
Yes. Can you hear me?
Yes.
Yeah, great. So I was wondering, like, could you tell us a bit more about the stack behind Data Trove? And are you like, I think you should be open to contributions, right?
Yes. So you can contribute, and people have been contributing. You can. Am I still sharing? Yes, I am. So as you can see here, there's quite a lot of contributors, and then some are from Hugging Face, obviously, but some are not. And basically, the whole thing is Python. So it's we try to have it like a very low barrier of entry library, so people can use it and understand what it does quite easily. Without, like we could try to optimize some things in Rust, in C++, whatever, but we just try to keep it to Python. So it's all Python, pretty much, you can see here. And yes, we are open to contributions.
Any other question?
Yes, I was really curious about the cost of small models training to evaluate test data.
So I'm not entirely sure, because like internally at Hugging Face we have a cluster. So I just launched the job. Like the GPUs are there; they're paid for, whether we use them or not. But it could be a bit costly. So I think like if you're working at a university, for example, and you have a cluster with a few GPUs, you might be able to train one of these models over a few days. I can tell usually I use 8 nodes that have, I think they have H100s. And it takes a few hours to train. So like it's basically on 64. Yeah, so it's a bit, if you like again, this is like a very capital intensive thing. So if you don't, it's not something you cannot pre-train models by yourself in your little laptop. I think it's unfortunately.
Any other question? Thank you, Guilherme, for the answer so far.
May I ask a second question?
Yeah, sure.
Yeah, okay, great. So I was wondering if you know of any experiments that involve like different architectures and transformers for controlling the quality of the data, like when you train a small model. Are you aware of certain people trying to assess quality with more like linear time models?
What do you mean? But what specifically? What models do you have in mind?
Like Member, for example.
Yeah, so I can tell you it's not specific on small models, but there are quite a lot of people training some Mamba models. And internally, I think I can tell you at Hugging Face, I'm actually working on a data set to train a Mamba model. We're still not sure about the scale, but it's something, yeah. So I think people are working on it, but in the end, like as I said in the beginning, there might be some small benefit in inference or training or whatever. It might be slightly cheaper, but overall performance will never be the big difference. Like if 2 models are trained on the same data transformer and a Mamba, I would not expect. So this is the experiment went to run, but I would not expect the Mamba to be much worse or much better.
Yeah, just I meant like just for the small models that you use to assess the quality of your data. Like, have we found that using this type of model also work, or because
it's
it
a good
could
question.
be expensive?
I see. So I mean, yeah. So there could certainly be something more on the like early signal part, where it's in the beginning would be better. So it's something to explore. Actually, I don't know if anyone trying to do this sort of thing, but it's an interesting question for sure. Yeah. Thanks.
Thanks.
Anyone else?
Yes, I have a question. Mistral is doing a great job, let's say, creating models which are very efficient, but hiding or not disclosing the way they train the data. Have we any ideas of the recipes they use to get those data, and are they among those you have been presenting to us, or are there some new ideas, new trends to improve the quality of data?
That's a great question. So and it's actually something that's quite important for me and for Hugging Face in general. So we don't know. I mean, there are always whispers. I mean, especially because like it's not a very big field, so you always know people who are working on different places. There are some whispers, but you don't know. Like, so obviously, like a big part of it should not be too different. There's some things that are more or less the same, like language filtering, some basic filtering, and so on. But there are, so like I've heard, for example, people say that they do some smart selection of data. So like, for example, when they are training, that some people have been doing something like this. They pack semantically similar data in the same batch, for example, or like the data set is not just randomly shuffled. They more or less try to pack things in a way that could optimize. So I've heard people say this. I don't know. I've heard people say they paid for some data. I don't know. Like you don't know, right? There's no way to know. Yeah, I mean, the thing that for sure they probably did is they really thought how to do, like, they really took data processing seriously, and didn't just like a lot of people just grab some data set that was already done and like, so I think they were careful, and they thought the thing through, and they were quite careful with what they did, whatever it was. And then obviously they probably trained on quite a lot of tokens.
Thank you, Guilherme. Any other question?
Yeah, I have one. So are these filtering and deduplication techniques also relevant for other languages, or are they working really well? For example, I'm mainly thinking about languages that do not have the same alphabet as English, like Arabic, Russian, Chinese.
So that's a great question, and one of the difficulties in adapting like this filtering, actually. So especially the spacing, because some languages do not have like a space as a separator of words, right? So some of the current code that we see in Data Trove expects there to be a space separating words, and we'll use that to create anagrams or whatever. And you cannot just apply that straight out of the box to these sort of languages. For example, the e-paper, so they have a lot of Chinese data, and I think they have some details on what they did. But you can look at different ways to separate. You can have a specific tokenizer for the language that will separate the words, for example, or you could try to do something on the byte level instead of on words level. So there are the different things you can do, but yeah, so you have to be careful, and most things will not work out of the box for these languages that are very different to English and to like a Latin alphabet and so on.
Go ahead,
Given the amount of companies and entities that can actually train those models, given the prices cost, I mean, very little, why do you think they do keep things like the number of tokens hidden?
I mean, so I guess they. So you mean like specifically for models that are released, I guess, or
Yes.
Yeah. So I mean, I think especially like with Mistral, for example, that's what they did a bit. Like they had this. They started out. They trained these very good models. They released them. They didn't. So in a way, to get some traction, to get some buzz, to get some adoption and name recognition. But now, like there's, I think they have a new model, or they work on some new models that will not be released. So in a way, it's a way to preserve their secret sauce. They're still a company. In the end, they're still for profit. They want to make money. They have investors that are counting on them to grow and so on. So you can just, I kind of understand the business incentives to not just give away everything. Even though I don't agree with, I think like we'd move forward much faster in general if everyone was sharing, everything. But I understand the incentives, and I think that's why you just don't want to give away your secret sauce like that. It's something that and it's an interesting trade-off, because they manage to get a lot of recognition without doing that, right? So they can still push out more models that are quite good, but it's not super easy for someone to come in and just replicate what they did. Yeah.
I have a second question, which is about synthetic data. You mentioned it in the beginning. Do we know the importance, I mean, the role that synthetic data could play in pre-training those models? I've seen that, for instance, stable LM2 contains some amount of synthetic data as well. Like, what's the current knowledge about it?
So it's not much. So I'd say so. This is another idea. So about the question before, what do they do different, like Mistral, one of these companies? So some people say that you could also just have a lot of synthetic data that you could take, like from GPT-4, for instance, right? So it's hard to say. I think it could work well for some specific things, or like especially for some, if you're doing some task-specific fine-tuning, whatever, and don't have a lot of data, you could try to have a bigger model generate something that would fit with your domain. But to me, the most interesting part is actually the smaller models, because the idea of if with this synthetic data, you could be very targeted and very focused on very high quality data that is like efficient in terms of like information density. And there's like there's a project called Cosmopedia, which is like an attempt to try to reproduce the Phi2 stuff that is not open. There's also an open Phi initiative. So to me, I think like at this small model level, it's quite interesting, because then it's something that you can run on your own computer, and if that is enough to make a small model be really good, that's interesting. Yeah.
Thank you very much.
I have one question as well. So let's keep talking about like filtering data for like curating data for pre-training. Do you think there is more work to do in adapting, fine-tuning, really using the existing filters? Do you think we actually have a lot of work to do on innovation of like new ways to filter, duplicate, curate, whatever? If you had to decide on like one direction to take pre-training data one step further, what's your best bet?
Okay. So maybe not further, but laterally, I would say that, and actually a lot of questions have been about this, multilingual data is still not something people work too much on. Like you just train a very big model in English or in code or whatever, and then you just make kind of ignore, maybe have a little bit in there, and usually have English and other languages in the same document, so it picks up a bit. But I'd say there's quite a lot of work to be done on adapting current knowledge, current pipelines and processes to different languages. So that would be one thing. In terms of like big innovations, I'm not sure there will be a lot, especially if we start from the same source. So currently, everything comes from Common Crawl. There's only so much cleaning you can do with that sort of data, right? So I'm not sure so, and then it also depends like on model, like on how. So there was some developments recently about like, for example, when we were training Falcon, we had a single epoch, and this was more or less what everyone was doing. You just get a lot of data, so you don't have to repeat anything. There have since been some papers where people have seen that maybe 4 epochs is okay, like you don't lose too much. So it's better to filter down more, because you can always filter down more. It's always a choice. You can always increase your thresholds, find some other filter that remove some other thing. Maybe it's better to filter down more and then just have a few more epochs on the same better data. Yeah, I think it depends a lot on use case by use case. But yeah, I would say for pre-training in general, there's not that much, especially because I think like the big differentiators for like model like GPT-4 and so on are on the alignment part and not so much on the pre-training part. It's actually interesting because there was a paper a while back where people, by asking ChatGPT to repeat, or GPT-4 to repeat poem a lot of times, it would actually spit out some pre-training data. And if you look at the data, it's just like noisy data. Like you have a footer with some guy's contact on it, like, so it's not like the data is amazing. I think like the big trick is all in the next stages.
Yeah, I agree. Okay, I think we have time for one last question before we close. Anyone?
Yeah, I have a question.
Yeah, go ahead.
Okay, so when you talked about the min hash for the duplication process and the bucket size, I mean, what are the things that we should like be considering when like choosing the size of the bucket?
Okay, that's a good question. So basically, the way it works, you have a list of numbers of hashes, right? And each document has the same number of hashes. And the idea is that if 2 documents are similar, then for the same position in the list, some of the numbers will be the same. So what you do then is that to make it easier to find these matches, because you could, if you were to compare, every pair, it would still be O(n) squared. What you do is you take this list and you split it into equal size chunks, and you say, okay, I'll say that there's a match if on this specific chunk, all the numbers match exactly, right? So instead of just counting how many match in the whole thing, you just say, okay, in this bucket. So by the way you are sampling, and I'm not sure if I probably have numbers here, but like, like the probability, like if you have 2 documents that are 80% similar, let's say, right? So the idea is that 80% of these numbers will match. So then you can compute the probability that they match on a given size. So for example, if you have like a bucket of 2 hashes, then the probability that they are the same, the documents are 80% similar, will be 0.8 squared, right? And then you can say, okay, but then what's the probability that they match on at least 1 bucket? And this will give you the probability of matching for a given similarity between them. So you can say, I want to try to match documents that are 70% similar, and with this you can size you can determine how many buckets you want to have, and basically the nice thing about this function of similarity, of like the probability of matching for a given similarity, is that it's almost a step. So basically there's more or less a value for which before this value of similarity it's very hard to have a match, and after this value it's quite likely. and the more hashes you have, the steeper this step is. But the more hashes you have, the more computation power you need to run this thing. So for example, for refined web, we were using 9,000 hashes, which is a lot. And I can tell you the default data trove implementation now has 120. So it's approximately the same threshold, but instead of like a step like this, it's more like this, you know? Yeah. And then another parameter that there is the size of n-grams. So for example, we take groups of 5 words, usually, and then we use these we hash them and we use them and so on, which, you know, like if you have a lot of interleaved text, but you have at least these 5 words, it's fine. If you increase this size, you'll only match things that have, like, for example, for 13 grams, if they have the same set of 13 words. So it's not as granular, but if you have a too small n-gram size, you'll be matching very common phrases, you know? So like, again, there's like a trade-off there. Yeah. Hope I answered the question.
Yeah.
Great. Thanks a lot, Guilherme. I think we can close here. Now, if you have questions about pre-training, you know who to annoy. He gave you all the context. I'll share the slides and the recording on the Meetup event, and it will probably be on LightOn social media as well. So yeah, stay tuned. And yeah, thanks a lot again. And
just one last thing.
Yeah.
Just one last thing. If you are a PhD student or you're conducting research and you want your research to be a little bit more known, you can contact us and keep the meetup going, and we'll organize one for the next time. Thank you very much.
Yep.
Bye.
Great. See you. Have a great day.
Thank you.
Bye-bye.
Bye.
See you. Bye bye.